Yes, I'm at Monash University, and I'm part. Melissa's probably told you about the Centre of Excellence for Climate Extremes, a new one, and there's 4 research programs, and I'm pretty active in the variability program. And we have a SAM cluster, so I'll explain what SAM is. And yeah, so if anyone's interested in kind of research in this area, then please let me know, and we can add you to the SAM cluster. Okay, so can I move forward? Yes. So this is basically what I want to cover today. So extratropical variability in the atmosphere. What is it? Why do we care about it? Is it changing? Can we simulate it with our climate models? And can we predict it? Can you hear me? Is it working? Yeah? Okay. So this is a nice diagram from the Bureau of Meteorology's website that talks about climate drivers in Australia. And you can see there's lots of tropical ones, ENSO, which Dietmar's going to talk to you about next. Madden-Julian oscillation, which is like 30 to 50 day timescale. The Indian Ocean dipole, which Dietmar will tell you isn't really a thing, but the Bureau uses it for prediction. And then the Southern Annular Mode is kind of the main mode of variability that we think about when we're looking at the Southern Ocean influence on Australian climate. I put that there because I just wanted to show you. Hang on, how do I do this? I wanted to kind of motivate you by looking at winds. There's this really nice satellite product of winds that you can get called the CCMP. You can just download these animations and the data. I think it's only available from, when does it start? 87 onwards. But it just shows you how strong the winds are in the Southern Ocean. And they're just really ripping across. I think it's satellite windstress, I think. I meant to look that up. This is wind speed, but I think it's at the surface, or near surface anyway. So, yeah, so it's just showing you lots of nice eddies forming in this Southern Ocean region. And you can see how zonally symmetric the jet stream is in the Southern Hemisphere. So it's really pretty constantly it sort of goes along a nice waveguide compared to the ones in the Northern Hemisphere, which are sort of sloping more in that northwest, southeast kind of direction. So yeah, I think there's lots of nice things that we could learn from watching that. But I will stop that. Okay. Yeah. So what is it? So I guess what I'm talking about today in terms of extratropical variability is this sort of large-scale hemispheric view. I think Michael Reeder probably talked to you about kind of variability on a sort of more local scale. And the main thing that we talk about when we're thinking of extratropical variability are these annular modes. So I did research on annular modes for a long time before I actually realized what and why it was called annular. And for those of you who don't know, an annulus is like a donut shape. So it's this longitudinally symmetric shape. And so that's why what I'll show you is the dominant mode of variability in the extratropics of both hemispheres. And so extratropics we think of as poleward of, say, 30 south. And unlike ENSO, which Dietmar will talk to you about, which involves coupled ocean-atmosphere interactions, the annular modes are just driven by internal variability of the atmosphere. So they don't really interact with the ocean at all in terms of the ocean influencing the atmosphere. The atmosphere does influence the ocean, but they're not coupled in that sense. And because of that, we can actually, you don't need any coupled ocean to simulate them. You can just have an atmospheric general circulation model with climatological sea surface temperatures, and you can get these annular modes. And they're called, there's a northern one, Northern Annular Mode, the NAM, and the Southern Annular Mode, the SAM. And they explain more of the variance on weekly, monthly, and yearly timescales in the extratropics than any other mode. It is, as I'll show you, a bit dependent on the time scale, the time of year, and the level in the atmosphere. But to first order, the SAM explains about 30% of the variance, and so it's kind of about similar for the, so if you're thinking about Australian rainfall. So yeah, it's an important thing to understand. So this is sort of different ways of depicting this Southern Annular Mode, and it is related to these winds that I just showed you in that animation. So it's basically, the annular mode is describing north and south shifts in the winds. So that happens on daily, weekly timescales, as well as changes on longer timescales. And it's also describing sort of the strength of those winds as well. And this is a zonal latitude height depiction. So the black contours here are the climatological position of the jet. So you can see we have these westerly winds. The jet stream centered around, say, 50 south, and they're strongest in the upper troposphere. And the SAM, so this is depicting a positive SAM position. The colours are showing a positive SAM, which is a shift poleward of the jet. And so you get increased winds here and decreased winds there if you shift poleward by a few degrees. And then this is sort of the surface depiction centered on Antarctica. So the positive SAM means you have lower pressure because of this shift of mass if you're shifting the jet stream, if that's not me. And so you get lower pressure over Antarctica and higher pressure over the mid-latitudes. And sort of a strengthening of this circumpolar vortex with a positive SAM. Yeah.
What is depicted in the second picture?
This is pressure, sea level pressure.
So just what, timing of the sea level pressure
For
DJF?
So this is just a schematic, but it's for, say, positive SAM in the DJF, yeah. But positive SAM in any season looks like this. It's lower pressure over Antarctica and high pressure here. And I think the next slide is giving some definition. So one of the confusing things that some people find about the SAM is that there's different ways of defining it, and different data sets used, different variables used. So there's two main ways. So one that's got a lot of traction since the sort of turn of the century, I guess, is this index of zonal mean sea level pressure differences between this mid-latitude region and the polar cap region. So this is the equation. You just look at sea level pressure anomalies at 40 south divided by their standard deviation, so it's normalized, and subtract the more poleward SAM. So it's basically choosing a zonal average around these latitudes, so 40 south minus 65 south. And this became quite popular because of the data issues we have in the Southern Hemisphere, especially over the Southern Ocean. There's really not any good data before the satellite era. And Antarctic data goes back to this IGY, International Geophysical Year. And so we can, Gareth Marshall at the British Antarctic Survey defined this index from observations so that we have actually an index of the SAM going back in time. Otherwise, we're kind of stuck from looking at the SAM only from 79 onwards, the satellite era. People have calculated the SAM from NSEP reanalyses further back, but no one really trusts them before the satellite era. So if you just take one thing away from this, please don't use reanalyses before the satellite era for the SAM. So yeah, this index by Marshall, you can get it on the web. You can download all the data. It's really easy to use, but it's just basically averaging, I think, 4 or 5 stations around the coast of Antarctica for that 65 south latitude, and then a few of these islands in the Southern Ocean. I think New Zealand gets one. Maybe he includes Hobart for the mid-latitudes. So you get this index then of the Southern Annular Mode. And you can see this is the monthly time series. It's got a lot of variability, and then he's got a sort of running mean to show that it has had some trends, which I'll talk about. So that's one way. No. The second way that's quite popular is to look at EOFs. So this is showing an EOF of 700 hectopascal geopotential height, again south of 20 South, so this extratropical region. And if you do an EOF analysis of that, you get this first EOF that looks very SAM-like, so it looks very annular. It's symmetric to a certain extent around sort of the Southern Ocean, mid-latitude region. And then you can look at the other EOFs, and you see that this dominant mode explains, I think it's 27.4% there, but it's around 30% of the variability of extratropical geopotential height. And if you want an index of that, they call it the AAO, the Antarctic Oscillation, which is the same thing, it's just a naming thing. But this is available from the NOAA website, and you can get a daily time series of the SAM, and they even have forecasts of it there, and they have long time series as well. So I think I'm going to talk a bit more about these EOFs later, about how, I guess, one of the benefits of EOFs is that compared to this, one disadvantage of this kind of index is that it's missing a lot of potential variability in the South Pacific because there's no stations there. And so that's one criticism of the SAM index from this Marshall method, whereas the EOF will capture all of the variability. And then this is just showing that, there's, if you look in the literature, there's, this Gong and Wang, the Marshall method, there's EOF methods, there's different heights, 850 heights, there's some people use sea level pressure, some people use winds, and then this is the correlation between them all. So to first order, they're fairly strongly correlated, particularly if you're looking at sort of the, I guess, if they're using the same method. But there are some differences people have to be aware of. I think that's, If you look over the satellite era there, they kind of line up fairly well. I thought I should briefly mention the Northern Annular Mode, just for completeness. So there's a similar mode in the extratropics of the Northern Hemisphere. There's been a lot of research on this. It's it's got sort of a strengthening of the polar vortex, is so colder polar vortex for positive phase, and there's been a lot of literature talking about the influence on surface temperatures in the Northern Hemisphere, and also a lot of research comparing it to the North Atlantic Oscillation, which again there's a lot of literature with you can get a longer record of that from the observations. The North Atlantic Oscillation is just a station between difference of pressure again between a station in Iceland and in the Canary Islands, I think. Again, you can get these sort of station-based data. This is the NAO, and you can see it's fairly similar to the NAM if you look at that EOF-based annular mode index. I did want to highlight that when I first got into research, there was a lot of discussion about trends in the NAO, and I think actually Dietmar mentioned this last year. So around the late 90s, when I was starting research, there was a few papers suggesting the NAO is trending positive, and this is what we expect under climate change, and what does it mean, and what's going to happen in the future. Oops. And but then if you look back, it sort of, after all these very prominent papers got published, it then suddenly went back down and started oscillating around. So I guess just a cautionary tale when we're thinking of the SAM and we don't have long records, we also want to be mindful that trends that we might be seeing, they could disappear. We don't want to infer too much from them. Okay, so this is the EOF, so Ghislaine Bochat, who's a postdoc at Monash gave me this, and she's been looking at the SAM and trying to be sort of have an objective view of how we think about the Southern Annular Mode. And so these are the EOFs for each season, so EOFs 1, 2, and 3, and you can see that it does differ between the seasons. So it probably looks the most zonally symmetric in DJF, and then in other seasons, particularly winter, it gets more of a sort of more asymmetry about it in the mid-latitudes, and looks like a zonal wave 3 pattern. And so if you are trying to think about the impacts of the SAM on our climate, then you want to understand how much of that extratropical variability really is driven by the SAM, or whether other modes are influencing the variability as well. So she's also been looking at planetary waves, so that's a different way of kind of looking at extratropical variability. So it's a Fourier decomposition into individual wave numbers. So zonal wave 0 is the SAM, so annular mode. And then you can decompose all of the variability in the extratropics into different waves. And I guess the idea with Fourier decomposition is that you have a time series and you kind of just decompose it into main waves, and then you could sum them all up and recreate what you started with. And there's a nice paper by Turner et al. In IJC, International Journal of Climatology, that looks at these waves and looks at their amplitude, phase, and variance, and also any trends that we might have seen over the last 30 years or so. So zonal wave 1 is this big one, and then zonal wave 3 is this one. And so and then Damien Irving at Melbourne Uni with Ian Simmons also had a few nice papers looking at these planetary waves. And yeah, if you read the literature, it's clear that zonal wave 2 doesn't really actually happen in reality. You never see it if you're looking at, say, those winds or heights. You actually never see this actually happening, so it's not a physically based wave. But zonal wave 3 we do see quite a lot, and I'll show you an example later of its impact on Antarctic sea ice. So Ghislaine's been looking at zonal wave 3 and thinking that when we're thinking about extratropical variability in the southern hemisphere, we want to consider both zonal wave 3 and the SAM, and how potentially zonal wave 3 is kind of modulating this annular kind of part of the SAM. So that's sort of some research that's going on right now. So in terms of that first question, what is it? So you can highlight these dominant modes of extratropical variability via these EOF analysis or Fourier analysis. And yeah, as I said before, you can simulate these annular modes in an atmospheric model just with climatological sea surface temperature. So you just have the seasonal cycle of sea surface temperature. You don't have any El Niños or anything going off. And so that implies it's a free internal mode that occurs in the absence of any external forcing, any boundary conditions from the SSTs. And yeah, it results from strong interactions between the time mean flow and the eddies superimposed on it. But there's a lot of research trying to understand why annular modes exist, and that it's not really settled how, why they form, why the jet moves north and south, what actually causes that. And yeah, the SAM is related to the position and strength of the mid-latitude eddy-driven jet. It occurs on all timescales, has a decorrelation timescale of 1 to 2 weeks. So it means it's not really very predictable beyond that sort of weather timescale. But I'll add a caveat to that later. And there's thought to be little impact from the underlying SSTs back onto the extratropical atmospheric variability, but there is some research going on in that. I think Dawn, is here somewhere? Yeah, he's looking at that in her PhD. Okay, so the next question is it changing? So this is a image from a figure from the latest ozone assessment report, which is coming out later this year. And the black lines are the SAM indexed based on that Marshall index, that station-based index of sea level pressure difference between 40 south and 65 south. And this is annual DJF, autumn, winter, and spring. And then the blue lines are from that animation of the winds, the CCMP winds, so the satellite winds. And what's shown here is the jet latitude, so the maximum latitude of the maximum strength of the winds. You pick that latitude and then you plot that every year. So you can see, if you look in most of them, most seasons, there tends to be some increase towards a more positive SAM and a more poleward jet location. But it's, yeah, so I think in the report there we say there's a poleward jet shift of about 0.5 degree per decade, but there's quite a bit of uncertainty in that, and it's predominantly in this austral summer season that you get that jet shift. And you can also see it's sort of, perhaps potentially in the jet latitude at least, it's not been trending quite as strongly in the last decade. Yeah, so it's satellite-based surface wind speed. I also wanted to put in a paleo context, so this is Nerali Abram, who's a CI here at ANU. A paper from her in 2014 was reconstructing the Southern Annular Mode Index back to 1000 AD. And you can see the last 50 years or so as being the most positive, as inferred from this reconstruction. This is, I think, from ice cores in Antarctica. But there's quite a lot of variability, and I think Nikki is looking at trying to understand this variability on these long time scales and whether there's some solar forcing or other forcing that might lead to this sort of decadal length variability.
How do you measure pressure, though, from ice cores?
I think it's temperature-based. Yeah. They infer it. Yeah, I think. Any other paleo people in the room? Yeah, I'm not. So, low remote. Yeah, I should know that, but I forget how they exactly do it. Yeah. And there is a more recent reconstruction Nerali's a co-author on that looks. So this is annual-based SAM, I think, and as I showed you, there's quite a bit of seasonality in the SAM, and they've done now a DJF reconstruction, and yeah, again, that shows the most positive period, I think, is in this last 50 years. But yeah, there's these parts are in that new reconstruction are really uncertain. So. Hey, so there was a nice paper by Swart and Fife in 2012 looking at trends in the SAM. This is based in the surface wind stress over the Southern Ocean in the reanalyses. So these are just over the satellite era, 79 to 2010, and it's hard to see these colours, but basically these are just trends in the latitude of the maximum surface wind stress. So this will be around 50 south, and so trends in that, and then trends in the strength of that wind stress. So is that maximum surface wind stress increasing? And each of the colours is a different season, and I think the black one is annual mean. So in all of the reanalysis, you get the strongest trends in the position in DJF, and they all are significant. Other seasons, particularly spring, is sort of not doing much. And trends in the strength are, some say positive and some say negative. So I think one thing to take away is that when we're thinking about these winds over the Southern Ocean, it's fairly robust across the reanalysis datasets and across that station-based SAM index, that there's been trends in the position of the jet, but really inconsistent trends in strength. I'm not going to talk much about the mechanisms for why we think this might occur, but I can refer you to, there's a really nice section in the ozone assessment report, which you can find online, from 2014, that kind of talks about the different theories for why we think a jet might move poleward. In this case, it's to do with ozone depletion, but it could also be to do with increasing greenhouse gases. But basically, for ozone depletion, it cools the stratosphere over Antarctica, That leads to stronger stratospheric westerly winds, an increase in potential vorticity, and an acceleration of the tropospheric zonal flow. But these simple model studies, they can't explain the magnitude of the observed shift we've seen, so there's some details still to be worked out of whether this mechanism can really explain the shift. There's also potential amplification from the tropospheric eddy feedbacks, and they've been tested in these idealized and comprehensive models, but there's still a lot of, there's no real settled mechanism for why we think this extratropical variability would change due to external forcing. But all models get it, so it's one of actually the most robust things you see in climate change models, that the jet shift, the southern hemisphere jet shifts poleward. But we don't actually understand why. And at AMOS, if any of you were at AMOS, we had a SAM cluster meeting, and Dave Thompson, who's kind of one of the pioneers of this Southern Annular Mode research, said that's probably his the main question he thinks people need to be working on is why, trying to come up with a mechanism. Okay, so why do we care about the SAM? So I've taught you a lot about what it is, but why do we care? Well, one reason is because it has a fairly strong impact on our surface climate over Australia. So this is a paper by Hendon et al., and it was just looking at composites of temperature and rainfall over Australia and the winds in the vectors for a positive SAM. So they looked at, I think, daily EOFs of geopotential height to define their SAM. So you can see that where the dots are solid, I think, or where the dots are shown there, if they're solid, they're significant. So you can see there's a significant impact on temperatures, and the shading here is a significant impact on rainfall. And this is for our summer. So if you have a positive SAM, the jet moves poleward, and that actually increases easterly flow over southern Australia, and that then leads to rainfall in the southeast increasing. But one of the confusing things about the SAM is that it varies quite strongly with season, in both sign and sign particularly. So if you're looking at winter, this is winter, autumn, spring and summer, you actually get drying with this positive SAM or a poleward shift in the jet, because it takes the sort of frontal systems away from southern Australia. So we get less rainfall in winter with a positive SAM, but then we get increased rainfall in the summer and spring seasons. So you always have to be cognizant of the season that we're looking at when we're thinking about the impacts. And then this is a more hemispheric view. Sorry, this is a bit small, but this is now for DJF and JJA, so summer and winter. And these are regressions of the SAM onto rainfall. So you see it's not just Australia that has a strong relationship with the SAM, but it's a broader hemispheric view. It's somewhat zonally symmetric if you squint a bit. And this study by Unpa Lim at the Bureau showed that the influence on the subtropical rainfall is much stronger in summer than winter, and that there's also, and that was mostly due to the fact that SAM and ENSO have some correlation in these austral warm seasons. Okay, in terms of extremes, I should have one slide on extremes since we're an extremes workshop. This is again from Ghislaine's work, looking at SAM regressions onto mean temperatures and then extreme temperatures. So this is the hottest day of the year, and this is for spring, and then this is the same on the bottom for Zonal Wave 3. And so you can see this cooling over Australia that we get for a positive SAM. You also get cooling over Antarctica, significant warming in the Southern Atlantic and southern South America. And then, interestingly, it seems very strong also with extreme temperatures, that you get that same pattern. And then this is the Zonal Wave 3 regression. And again, you see significant relationship between Zonal Wave 3 and mean temperatures, and perhaps even an amplification of that if you're looking at the extreme temperatures. particularly over Australia. So there's also some nice kind of examples where the SAM has really influenced some of our biggest extremes over Australia. And so this is the wettest spring that we had on record, so 115 or so years in our record of, actually I guess for rainfall maybe we only have 60 years, I think. But anyway, we had our wettest spring on record in 2010, and that then led into some major, that sort of primed the surface for some flooding later on in the summer. And the paper that I was co-author on, a few papers, looked at this rainfall anomaly over Australia, and this is the actual observed anomaly. And this is what we would have expected from La Nina. So there was a strong La Nina at the time, and you can see that, as we know, or Dietmar will tell you, leads to increased rainfall over Australia. But it was much, the rainfall we had was much larger than we would have expected from the strength of that La Nina. And so this study showed that the pattern of the SAM, which was really strongly positive at that time, so this is sea level pressure, the observation of sea level pressure for that spring 2010. This is what we'd expect from La Nina, and then this is what we expect from SAM. And so you can see the observed pattern really looked very SAM-like. And so that in the paper we talk about how this SAM, strong SAM, really enhanced the impact from that La Nina. So kind of this compound contribution of both of those modes really can, if they coexist, can really lead to some major extremes. Then we also looked at the hottest September on record in 2013, and this is what the observed pattern was. And in this paper we did a multiple linear regression of all the potential climate drivers we could think of that might have contributed to that extreme temperature. There wasn't much going on in terms of El Nino Southern Oscillation or the Indian Ocean Dipole, but there was again a strongly negative SAM that then led to warming, and that contributed to that extreme record. And we say in the paper about 20% was due to the positive SAM, negative SAM. There's also impacts on the Southern Ocean circulation, and so Andy Hogg's done a lot of research on this, where if you have this shift or strengthening of those westerlies in the Southern Ocean, then that leads to Ekman transport, so it leads to some cooling at the surface, poleward of that, and warming to the north. And then that actually has a signature in the ocean as well. So it intensifies the subtropical ocean gyres and the meridional overturning circulations and leads to some warming down there. So there's lots of reasons why we care about the SAM. There's also some impacts on the carbon cycle, which I won't go into. But yeah, since we're talking about the ocean, I'd put in a sea ice figure. And this is one from spring 2016. And you can see in the colours, this is the sea ice anomaly. So you can see a really strong reduction of sea ice compared to what normal conditions across sort of all ocean basins. And this is the time series since 2000 of Antarctic monthly sea ice extent. And so you can see it really dropped in 2016 to this record low that hadn't been ever seen before in the satellite era. And it has recovered a little bit since then, but it's still well below normal. And some papers I'm involved in that are both submitted now suggest that this drop in Antarctic sea ice was obviously driven by the atmosphere initially because it happened so rapidly. And there was, at the time, there was a record a month and sea low, so that's somewhere here. Record negative Indian Ocean Dipole, strong Zonal Wave 3 pattern, and a near record negative SAM later in the season. And so all of these, again, these climate drivers, these modes of variability kind of combine together, we argue, to lead to this record negative or drop in sea ice extent. But as you see, it's continued to stay low, so the second paper I'm involved in is suggesting maybe some decadal variability, maybe we've shifted into a new regime of lower sea ice extent. But we'll see what the reviewers say. Okay, so that's why we care. Can we simulate it? Is the next question. And so this is more focused on the trends that we've seen in the winds. So this latitude height picture I was showing before, this is from the JRA reanalysis. So again, in the black lines, you can see the climatological position of the jet, and in the reanalysis over that satellite era, you can see that there's been a shift poleward. And then these are all chemistry climate models and CMIP5 models, so sort of the IPCC type models. This is actually from 60 to 2000. And you can see they all kind of simulate pretty well what the reanalysis suggests has happened. So in terms of the trends, climate models can reproduce these trends if they're driven by the natural and anthropogenic forcings. And this paper was trying to see whether if we have interactive chemistry in the stratosphere so that we really simulate the ozone hole better, or if we have a coupled ocean, do we get a better representation of that jet shift? And the conclusions is that it doesn't make any difference. So these jet shifts are really driven by sort of things going on in the atmosphere. This is again looking at the SAM relationship to rainfall in the models. So I showed you the observations before. And I guess the conclusions are here that they can get this zonally uniform rainfall response in the extratropics. These are CMIP5 models. They do get the enhanced subtropical rainfall in summer, so that's in here. And they don't get it in winter, so that's similar to the observations. But they don't get the subtropical rainfall sensitivity to the covariability of SAM and ENSO, and they don't get the seasonality of this SAM and ENSO relationship. So I'll just show you, I think, here. So this, I think, is a really important thing when we're thinking about our climate models. So the black line is the observations, and this is season along the bottom, so January, February, March, April, all the way to DJF. So you can see that SAM and ENSO are correlated most strongly, and I think only significantly, in sort of late spring, early summer. But if you look at all the different models, all the different lines are from individual models, the correlation of El Nino 3.4, so ENSO and SAM. None of them get this seasonality in that relationship. And the multi-model mean it's just flat and insignificant. So it's a real weakness, I think, in our models that we're not getting this relationship. Or perhaps, we don't understand enough about the observations and whether that really exists on kind of, maybe there's some phase of decadal variability that's really driving this relationship. But something I think we need to look into. Can we simulate the trend in the SAM and what's causing it? So this one was showing you all of natural forcings and anthropogenic forcings combined. We can simulate it. If we look at the individual forcings, this is a paper by Gillett et al., I think. If we're looking at the SAM trends, again, from 50 to 2011, and all of the different colours are different forcings, so greenhouse gases, aerosols, ozone, natural. The black bars are the observations. So if we're looking at DJF, where we've had the strongest observed trends, then you can see that in the models, at least, ozone is the dominant driver. So the stratospheric ozone depletion over Antarctica has driven this SAM trend, according to these models. Greenhouse gases also contribute some part, but I would say, it's still unclear how much is due to greenhouse and gases and how much is due to ozone depletion. There has also been some work showing by Zoe Gillett, who submitted this paper to Journal Climate. So this is the trends in surface temperature, and this is how much is congruent with the SAM. So how much of this trend in surface temperature can we explain from the trend in the SAM, so a fair portion. And then she's looked at some coupled model runs to see how much the model suggests is due to ozone and how much is due to greenhouse gases. And you can see the ozone-induced response is much, sort of more realistic than the greenhouse gas one. And another student who's at Monash, who just submitted her master's thesis, was looking at rainfall trends and how much they can be explained by the SAM. And so the red line is the rainfall trends from different data sets, era interim reanalysis and the GPCP, if you just look at the top line. And the blue line is how much of those rainfall trends are due to the SAM. So you can see this sort of poleward shift is congruent with the SAM trend in both these data sets, with some degree of difference between them. And I just included this one mostly because I wanted to highlight there's these really spurious trends if you extend these trends. So this is 79 to 2000, this is 79 to 2016. If you extend these trends for a longer period, you get these really wacky rainfall trends over the Southern Ocean. So even this observationally sort of based data set, we just, don't necessarily trust over the Southern Ocean. So one difficulty working in the extratropics of the Southern Hemisphere that we have to be aware of is that the data sets and the reanalysis are really, we have to use them with a lot of caution. And this, I think, is due to an introduction of a new satellite in around 2000 that really messed up the rainfall. How am I going? 2 minutes. Okay, I might just skip this bit. But just to say that we think the ozone hole is starting to recover. So it's sort of been plateauing, and perhaps part of this sort of fact that the jet's not really been shifting poleward in the last decade perhaps is a sign of ozone recovery, so that it's not continuing to shift at poleward, but there's a lot of uncertainty in whether the ozone hole is actually starting to recover, and I would say there's a lot of variability in these winds, so they may, as I said before, that note of caution, they may start trending positive again soon. Okay, and the last thing I wanted to talk about is, can we predict it? So these are figures from the Bureau of Meteorology's a seasonal prediction system. This is again just what we expect from positive SAM in summer and winter in terms of rainfall. So increase in summer with positive SAM and decrease in winter. And then the Bureau has an experimental SAM index forecast that they look at what's going to happen with the SAM. And in their new seasonal prediction system, Access S1, in the red compared to the green, which is Poema, you can see the skill here. So the higher the number here, the better the skill in the forecast. And this is lead time, so predictions out to 35 days. So you can see we get skill, say when it drops down below 0.5, it's probably not useful anymore, but we do get skill out to about 15 days, and the skill has improved with the new seasonal prediction system. And just wanted to, again emphasise that SAM is significantly correlated with ENSO, and Zoe's work has shown potentially, if we can look at the size of the ozone hole in late spring, we could use that to extend the predictions for the SAM a bit longer. So that there is some potential in certain seasons to maybe have a longer term prediction of the SAM. And I think I'll end there. Okay. Okay, so the Southern Annular Mode and mid-latitude westerlies have broad impacts across the Southern Hemisphere, which vary seasonally. And I should have said that the Southern Annular Mode is, just to remind you, if that's the largest mode of extratropical variability. I've also talked about Zonal Wave 3 as well. And we have seen these poleward shifts in the westerly winds and the SAM in austral summer mostly, but there is observational uncertainty about that. SAM trends in that austral summer season have been linked primarily to ozone depletion, and there's the associated impacts that has on surface climate and the Southern Ocean and Antarctic sea ice. And then I finish with sort of some of these record SAM events have been linked to record spring rainfall and temperatures in eastern Australia, as well as the recent Antarctic sea ice decline. And that there is some potential for seasonal prediction of the SAM via links with ENSO and ozone, and then some work in the Bureau of Meteorology looking at sort of stratospheric influence as well to extend that prediction. And then, yeah, I skipped over this, but future changes will really depend on the balance between ozone recovery and greenhouse gases. So in the future, ozone recovery will try and shift the SAM negative or the jet more equatorward, and greenhouse gases will keep pushing it poleward. So there's going to be this tug of war between those two external forcings going forward. Okay, that's it. Thank you.
So you were saying before that a positive SAM event will be correlated with the decrease in temperatures over spring, which I found a little bit surprising because I would have imagined that even during that time of year, if you had a negative SAM, you would have more storms reaching the mainland and therefore cooler air pushing through. I'm just wondering how that mechanism might work to actually cool the temperatures down over central Australia or most of the continent.
Yeah, good question. So I think a lot of it is due to the covariability of rainfall and temperature. So if you have, this is positive SAM, you get sort of increased rainfall in the southeast, and so then that leads to cooler conditions. Then I think in the paper they talk also about cloudiness, I think, is part of it as well. So you, you'll get sort of a relationship with that. I think in the southwest the relationship's a bit different in terms of temperature, and it's due to sort of radiative effects. Okay.
You showed the slide that the outstanding mechanism to be explained.
That one?
So you were saying, you mentioned something, Dr. Thompson said in the previous round that this is the most important thing to address, which?
The mechanism, yeah. So the mechanisms proposed at the moment, they don't explain the magnitude of the shifts that we've seen, and so they're sort of, not really fitting with the observations. So I guess there's a lot of different ideas of what the mechanisms.
Somewhere a review of these mechanisms in the literature.
Yeah, there's a good one by Ed Gerber. And if you go to the ozone assessment report, there's a really nice summary from 2014. There's a new ozone assessment report. I can send it to you. Maybe. Yeah. It talks about sort of the outstanding questions.
Could you just expand a little bit on how SAM is affected by the ozone hole?
Yeah, sure. I did skip over that for time. I think I have, right at the end I put in so in terms of so this is kind of, there's cooling in the polar stratosphere. So ozone causes warming, and so if you deplete the ozone, then you have cooling happening in the polar stratosphere, and then that basically steepens the meridional temperature gradient between the tropics and the pole, and so then that, that's sort of the simple kind of explanation, is that then shifts the westerly winds poleward. Greenhouse gases also shift the westerly winds polar because they warm the troposphere more than they warm the polar region, and so then you also steepen this meridional temperature gradient, and that also shifts the winds poleward. Was that your question? Yeah. So this is kind of a schematic of all the kind of impacts of ozone depletion. So it accelerates the stratospheric overturning circulation. There's a lot of studies suggesting it expands the Hadley cells, so we have more subtropical drying. It's basically expanding the tropics. And then forward to that, you get increased subtropical rainfall. I'm getting confused. So, but yeah, southward shift of the mid-latitude rain and the winds. And then Antarctica, it's a bit unclear how the poleward shift of the westerlies are influencing the sea ice around Antarctica. Because all of the models suggest the sea ice should be melting, and the sea ice hasn't melted until last year. And so the role of ozone depletion on Antarctic sea ice is really quite still an outstanding question. Because the models and the observations don't agree. Yeah. Okay. Thanks, guys.